Bessel functions, first defined by the mathematician Daniel Bernoulli and generalized by Friedrich Bessel, are the canonical solutions y, x, of Bessel's differential equation. For an arbitrary complex number I plus or minus. The most important cases are for I plus or minus an integer or half-integer. Although I plus or minus and ai plus or minus produce the same differential equation for real I plus or minus, it is conventional to define different Bessel functions for these two values in such a way that the Bessel functions are mostly smooth functions of I plus or minus. Bessel functions are also known as cylinder functions or the cylindrical harmonics because they appear in the solution to Laplace's equation in cylindrical coordinates. Applications of Bessel functions. Bessel's equation arises when finding separable solutions to Laplace's equation and the Helmholtz equation in cylindrical or spherical coordinates. Bessel functions are therefore especially important for many problems of wave propagation and static potentials. In solving problems in cylindrical coordinate systems, one obtains Bessel functions of integer order. In spherical problems, one obtains half-integer orders. For example, electromagnetic waves in a cylindrical waveguide, pressure amplitudes of inviscid rotational flows, heat conduction in a cylindrical object, modes of vibration of a thin circular artificial membrane, diffusion problems on a lattice, solutions to the radial Schrödinger equation for a free particle, solving for patterns of acoustical radiation, frequency-dependent friction in circular pipelines, dynamics of floating bodies. Bessel functions also appear in other problems, such as signal processing. Definitions. Because this is a second-order differential equation, there must be two linearly independent solutions. Depending upon the circumstances, however, various formulations of these solutions are convenient. Different variations are described below. Bessel functions of the first kind are G plus or minus. Bessel functions of the first kind, denoted as G plus or minus, x, are solutions of Bessel's differential equation that are finite at the origin, z equals a0, for integer or positive I plus or minus, and diverge as x approaches 0 for negative non-integer I plus or minus. It is possible to define the function by its Taylor series expansion around z equals a0. Where I, z, is the gamma function, a shifted generalization of the factorial function to non-integer values. The Bessel function of the first kind is an entire function if I plus or minus is an integer, otherwise it is a multi-valued function with singularity at 0. The graphs of Bessel functions look roughly like oscillating sine or cosine functions that decay proportionally to 1 per RSHx, although their roots are not generally periodic, except asymptotically for large x is the derivative of Jo, x, much like a sin, x, is the derivative of cos, x. More generally, the derivative of Jn, x, can be expressed in terms of Jn a plus or minus 1, x, by the identities below. For non-integer I plus or minus, the functions g plus or minus, x, and ji plus or minus, x, are linearly independent, and are therefore the two solutions of the differential equation. On the other hand, for integer order I plus or minus, the following relationship is valid. This means that the two solutions are no longer linearly independent. In this case, the second linearly independent solution is then found to be the Bessel function of the second kind, as discussed below. Bessel's integrals, another definition of the Bessel function, for integer values of n, is possible using an integral representation. Another integral representation is. This was the approach that Bessel used, and from this definition he derived several properties of the function. The definition may be extended to non-integer orders by greater than 0, one of Recurrence-Flee's integrals. Relation to hypergeometric series, the Bessel functions can be expressed in terms of the generalized hypergeometric series as. This expression is related to the development of Bessel functions in terms of the Bessel-Euro-Clifford function. Relation to Laguerre polynomials, in terms of the Laguerre polynomials Lk and arbitrarily chosen parameter t, the Bessel function can be expressed as. Bessel functions of the second kind are y plus or minus, the Bessel functions of the second kind, denoted by y plus or minus, x, occasionally denoted instead by ni plus or minus x, are solutions of the Bessel differential equation that have a singularity at the origin. Bessel functions of the second kind are multivalued with singularity at 0. These are sometimes called Weber functions after Heinrich Martin Weber, and also Newman functions after Carl Newman. For non-integer I plus or minus, y plus or minus, x, is related to g plus or minus, x, by. In the case of integer order n, the function is defined by taking the limit as a non-integer I plus or minus tends to n. There is also a corresponding integral formula greater than 0. Y plus or minus, x, is necessary as the second linearly independent solution of the Bessel's equation when I plus or minus is an integer. But y plus or minus, x, has more meaning than that. It can be considered as a natural partner of g plus or minus, x. See also the subsection on Hankel functions below. When I plus or minus is an integer, moreover, as was similarly the case for the functions of the first kind, the following relationship is valid. Both g plus or minus, x, and e plus or minus, x, are holomorphic functions of x on the complex plane cut along the negative real axis. When I plus or minus is an integer, the Bessel functions j are entire functions of x. If x is held fixed at a non-zero value, then the Bessel functions are entire functions of I plus or minus. The Bessel functions of the second kind when I plus or minus is an integer is an example of the second kind of solution in Fuchs's theorem. Hankel functions, high plus or minus 1, high plus or minus 2, another important formulation of the two linearly independent solutions to Bessel's equation are the Hankel functions high plus or minus 1, x, and high plus or minus 2, x, defined by. Whereas the imaginary unit. These linear combinations are also known as Bessel functions of the third kind. They are two linearly independent solutions of Bessel's differential equation. They are named after Hermann Hankel. The importance of Hankel functions of the first and second kind lies more in theoretical development rather than in application. These forms of linear combination satisfy numerous simple-looking properties, like asymptotic formulae or integral representations. Here, simple means an appearance of the factor of the form if, x. The Bessel function of the second kind then can be thought to naturally appear as the imaginary part of the Hankel functions. The Hankel functions are used to express outward and inward propagating cylindrical wave solutions of the cylindrical wave equation, respectively. Using the previous relationships they can be expressed as: if I plus or minus is an integer, the limit has to be calculated. The following relationships are valid, whether I plus or minus is an integer or not. In particular, if I plus or minus equals m plus 1/2 with m a non-negative integer, the above relations imply directly that. These are useful in developing the spherical Bessel functions. The Hankel functions admit the following integral representations for e, x, 0. Where the integration limits indicate integration along a contour that can be chosen as follows, from a to 0 along the negative real axis, from 0 to a plus or minus e euro along the imaginary axis, and from a plus or minus e euro to plus a plus or minus e euro along a contour parallel to the real axis. Modified Bessel functions e plus or minus, key plus or minus, the Bessel functions are valid even for complex arguments x, and an important special case is that of a purely imaginary argument. In this case, the solutions to the Bessel equation are called the modified Bessel functions of the first and second kind, and are defined by: when I plus or minus is not an integer. When I plus or minus is an integer, then the limit is used. These are chosen to be real-valued for real and positive arguments x. The series expansion for e plus or minus x is thus similar to that for g plus or minus x, but without the alternating factor. If a I euro arg x, a per mil currency I euro /2, key plus or minus x, can be expressed as a Hankel function of the first kind. And if I euro /2, arg x, a per mil currency I euro, it can be expressed as a Hankel function of the second kind. we can express the first and second Bessel functions in terms of the modified Bessel functions of per mole currency I/2. Li plus or minus x, and Ki plus or minus x, are the two linearly independent solutions to the modified Bessel's equation. Unlike the ordinary Bessel functions, which are oscillating as functions of a real argument, Li plus or minus and Ki plus or minus are exponentially growing and decaying functions, respectively. Like the ordinary Bessel function G plus or minus, the function E plus or minus goes to 0 at x equals 0 for I plus or minus 0 and is finite at x equals 0 for I plus or minus equals 0. Analogously, Ki plus or minus diverges at z equals a0. Two integral formulas for the modified Bessel functions are greater than 0. Modified Bessel functions k1/3 and k2/3 can be represented in terms of rapidly converged integrals. The modified Bessel function of the second kind has also been called by the now rare names, Bassett function after Alfred Barnard Bassett, modified Bessel function of the third kind, modified Hankel function, MacDonald function after Hector Munro MacDonald, Weber function, Newman function, spherical Bessel functions, Jn, in. When solving the Helmholtz equation in spherical coordinates by separation of variables, the radial equation has the form. The two linearly independent solutions to this equation are called the spherical Bessel functions Jn and in, and are related to the ordinary Bessel functions Jn and in by. In is also denoted Nn or In. Some authors call these functions the spherical Newman functions. The spherical Bessel functions can also be written as the first spherical Bessel function Jo, x, is also known as the sinc function. The first few spherical Bessel functions are and generating function. The spherical Bessel functions have the generating functions. Differential relations. In the following Fn is any of four spherical Hankel functions, Hn, 1, Hn, 2, there are also spherical analogues of the Hankel functions. In fact, there are simple closed-form expressions for the Bessel functions of half-integer order in terms of the standard trigonometric functions, and therefore for the spherical Bessel functions. In particular, for non-negative integers n, and is the complex conjugate of this. It follows, for example, that and so on. The spherical Hankel functions appear in problems involving spherical wave propagation, for example in the multipole expansion of the electromagnetic field. Recurrence Bessel functions, Sn, Cn, I3/4 n, I paragraph n, Recurrence Bessel functions only slightly differ from spherical Bessel functions. They satisfy the differential equation. This differential equation, and the Recurrence Bessel solutions, arises in the problem of scattering of electromagnetic waves by a sphere, known as my scattering after the first published solution by my. See for example, do for recent developments and references. Following debut, the notation is sometimes used instead of asymptotic forms. The Bessel functions have the following asymptotic forms. For small arguments, one obtains when I plus or minus is not a negative integer. When I plus or minus is a negative integer, we have. For the Bessel function of the second kind we have three cases. Where I cubed is the Euler or Euro-Mascaroni constant. For large real arguments, one cannot write a true asymptotic form for Bessel functions of the first and second kind because they have zeros all the way out to infinity which would have to be matched exactly by any asymptotic expansion. However, for a given value of arg, z, one can write an equation containing a term of order ZA1. For I plus or minus equals January 2nd, the last terms in these formulas drop out completely. See the spherical Bessel functions above. Even though these equations are true, better approximations may be available for complex z. For example, Jo, z, when z is near the negative real line is approximated better by than by. The asymptotic forms for the Hankel functions are. These can be extended to other values of arg, z, using equations relating into high plus or minus 1, z, and high plus or minus 2, z. It is interesting that although the Bessel function of the first kind is the average of the two Hankel functions, g plus or minus, z, is not asymptotic to the average of these two asymptotic forms when z is negative used. But the asymptotic forms for the Hankel functions permit us to write asymptotic forms for the Bessel functions of first and second kinds for complex z so long as z goes to infinity at a constant phase angle arc z. For the modified Bessel functions, Hankel developed asymptotic expansions as well. When I plus or minus equals 1/2, all the terms except the first vanish and we have. For small arguments, we have properties. For integer order I plus or minus equals n, Jn is often defined via a Laurent series for a generating function. An approach used by P. A. Hansen in 1843. Another important relation for integer orders is the Jacobi-Euro-Anger expansion, and which is used to expand a plane wave as a sum of cylindrical waves, or to find the Fourier series of a tone-modulated FM signal. More generally, a series is called Newman expansion of E. The coefficients for I1/2 equals 0 have the explicit form, where OC is Newman's polynomial. Selected functions admit the special representation with, due to the orthogonality relation. More generally, if E has a branch point near the origin of such a nature that, then, or, where is F's Laplace transform? Another way to define the Bessel functions is the Poisson representation formula and the Milesonian formula, where I1/2 are 1/2 and Z are C. This formula is useful especially when working with Fourier transforms. The functions g plus or minus, y plus or minus, high plus or minus, 1, and high plus or minus, 2, all satisfy the recurrence relations, where Z denotes J, Y, H, 1, or H, 2. In this way, for example, one can compute Bessel functions of higher orders given the values at lower orders. In particular, it follows that modified Bessel functions follow similar relations and the recurrence relation reads, where psi plus or minus denotes E plus or minus or E plus or minus I euro IKI plus or minus. These recurrence relations are useful for discrete diffusion problems. Because Bessel's equation becomes Hermitian if it is divided by x, the solutions must satisfy an orthogonality relationship for appropriate boundary conditions. In particular, it follows that where I plus or minus are 1, Im, n is the Kronecker delta, and E plus or minus, m is the MTH0 of G plus or minus, x. This orthogonality relation can then be used to extract the coefficients in the Fourier-Gyro Bessel series, where a function is expanded in the basis of the functions g plus or minus, x e plus or minus, m, for fixed I plus or minus and varying m. An analogous relationship for the spherical Bessel functions follows immediately. If one defines a boxcar function of x that depends on a small parameter I micron as where rect is the rectangle function, then the Hankel transform of it, gi micron, k, approaches g plus or minus, k, as I micron approaches 0, for any given k. Conversely, the Hankel transform of gi micron, k, is phi micron, x, which is 0 everywhere except near 1. As I micron approaches 0, the right-hand side approaches I, Z1, where I is the Dirac delta function. So by abuse of language, one says that even though the integral on the left is not actually defined, a change of variables then yields the closure equation. For I plus or minus a 1/2, the Hankel transform can express a fairly arbitrary function as an integral of Bessel functions of different scales. For the spherical Bessel functions the orthogonality relation is for I plus or minus a 1. Again, this is a useful formal equation whose left-hand side is not actually defined. Another important property of Bessel's equations, which follows from Abel's identity, involves the Wronskian of the solutions, where I plus or minus and B plus or minus are any two solutions of Bessel's equation, and psi plus or minus is a constant independent of x. In particular, and There are a large number of other known integrals and identities that are not reproduced here, but which can be found in the references. Multiplication theorem. The Bessel functions obey a multiplication theorem. Where I and I1/2 may be taken as arbitrary complex numbers, see the above expression also holds if is replaced by. The analogous identities for modified Bessel functions are and. Burgett's hypothesis. Bessel himself originally proved that for non-negative integers n, the equation Jn, x, equals 0 has an infinite number of solutions in x. When the functions Jn, x, are plotted on the same graph, though, none of the zeros seem to coincide for different values of n except for the 0 at x equals 0. This phenomenon is known as Burgett's hypothesis after the 19th-century French mathematician who studied Bessel functions. Specifically it states that for any integers n per mil 0 yen and m per mil 1 yen, the functions Jn, x, and Jn plus m, x, have no common zeros other than the one at x equals 0. The hypothesis was proved by Carl Ludwig Siegel in 1929. Selected identities. See also, Anger function, Bessel-Euro-Clifford function, Bessel polynomials, Fourier-Gyro Bessel series, frequency modulation, Hanau-Euro-Exton Q Bessel function, Hankel transform, Jackson Q Bessel function, Kelvin functions, Lerchia-Euro-Neuberger sum rule, Lommel function, Lommel polynomial, Newman polynomial, propagator, Sonine formula, Streff function, vibrations of a circular drum, Weber function, Wright generalized Bessel function, notes. References, Abramowitz, Milton. Stegun, Irene A., eds., Chapter 9, Handbook of Mathematical Functions with Formulas, Graphs, and Mathematical Tables, New York, Dover, PA 355, ISBN A978-0486612720, MRO 167642AA See also Chapter 10. ARFKEN, George B. and Hans J. Weber, Mathematical Methods for Physicists, 6th edition. ISBN 0-12-059876-0. Bain, S.S. Mathematical Methods in Science and Engineering, Wiley, 2006, Chapter 6. Bain, S.S., Essentials of Mathematical Methods in Science and Engineering, Wiley, 2008, Chapter 11. Bowman, Frank Introduction to Bessel Functions. ISBN 0-486-60462-4. G. Mai, Byte Recurrency G. Isa Optique Tra 1 Quarterber Medien, Speziell Colloidal Metalle Paragraph Sungen, Ann. Viz. Leipzig 25, PA 377. Ulver, F. W. J. Maximum, L. C., Bessel Function, in Ulver, Frank W. J. Lozier, Daniel M. Berweiswert, Ronald F. Clark, Charles W., NIST Handbook of Mathematical Functions, Cambridge University Press, ISBN A978-0521192255, MRA 2723248 Press, W.H. Tucholsky, S.A. Bettling, W.T. Flannery, B.P., Section 6.5. Bessel Functions of Integer Order, Numerical Recipes, The Art of Scientific Computing, New York, Cambridge University Press, ISBN A978-0-521-88068-8. B. Spain, M. G. Smith, Functions of Mathematical Physics, Van Nostrand Reinhold Company, London, 1970. Chapter 9 deals with Bessel functions. NM-TEM, Special Functions. An Introduction to the Classical Functions of Mathematical Physics, John Wiley & Sons, Incorporated, New York, 1996. ISBN 0-471-11313-1. Chapter 9 deals with Bessel functions. Watson, G.N., A Treatise on the Theory of Bessel Functions, 2nd edition, Cambridge University Press. ISBN 0-521-48391-3. External links: Lizorkin, P.I., Bessel functions, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Kamazina, L.N. Prudnikov, A.P., Cylinder function, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Razov, =NKH, Bessel equation, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Wolfram function pages on Bessel J and Y functions, and modified Bessel I and K functions. Pages include formulas, function evaluators, and plotting calculators. Wolfram MathWorld Gyro Bessel functions of the first kind, Bessel functions G1/2, U1/2, E1/2 and Q1/2 in Libro Function Handbook.